Okay, so far we have been talking about different types of FIR filters and their properties and what role the zeros play, but we have not really talked about if I am interested in a desired frequency response, how do I design an FIR filter? How do I create an FIR filter that satisfies that desired response? Okay. So for that, we'll learn the method of windowing. That is just one of the ways of designing FIR filters. If you go back to your screen about FDA tool that we have been using, actually you see a number of other options, but we will not cover those here. So how do you systematically design FIR filters? The first step is that you understand what your application needs, whatever application you are working with in seismology or you are working in music industry or whatever, you understand the ideal response that you need. So understand the needs of the application and come up with a desired filter and frequency response. So what you will have is that you say, I want a filter whose frequency response is HD to the J omega, whatever it looks like. It could be, for example, you could end up with your desired frequency response could be, let's say, a perfect low pass filter, right? Or it could be a crazy shaped filter based upon the needs of your application, right? Whatever is the response, you come up with that. That is on your paper or MATLAB or whatever formulation you have. And that is associated with, if you do the Fourier transform, an impulse response. So that is easy, right? So you take the inverse Fourier transform of your desired response and you get the impulse response. But of course that impulse response, so HD of n will likely not be an FIR filter. I.e., it will have infinite duration. Okay. For example, if you said my ideal filter is a low pass filter, then we know that the impulse response of that ideal low pass filter is a sink. Now sink goes from minus infinity to infinity. So you cannot use that as an FIR filter. It doesn't have finite duration. Now our goal is that we want to start with this desired impulse response HD of n and go to an FIR filter let's call it HT of n that is causal and we'll make it linear phase and real valued. So real valued, of course, is a function of your whether HD of n is real valued or not. Let's assume that that is the case. Linear phase is also trivial to achieve as long as you are symmetric or anti-symmetric, you will end up with a linear phase, so that is also easy. Causality is easy also because if you end up with a non-causal filter, you just shift it. So the main challenge is how do we go from these infinite number of filter taps, these filter coefficients, to a finite number of filter coefficients. That's the main challenge. Okay? So to do that, let's understand that ht of n also has some frequency response. Let's call it ht of e to the j omega. What we are after is, this is our ideal impulse response, and this is the ideal frequency response. We want to go from here to a finite impulse response, but what is the condition that we need? What we want is that our new frequency response, because once we are only using a finite number of values, our frequency response cannot be the same that we started with. But our goal is somehow our new frequency response should be as close to the ideal one as we can get. So our goal is design ht of n from hd of n such that ht of e to the j omega is close to the desired frequency response hd of e to the j omega. Okay? Now, how do we measure closeness then? So, the way we measure closeness is using the mean squared error formula. So, we define closeness. Let's call it FIR. That is defined as 1 over 2 pi minus pi to pi ht of e to the j omega minus hd of e to the j omega absolute squared d omega. So what you are doing is you are looking at, first of all, you are computing the absolute square difference between the ideal frequency response and your new frequency response, and then you are summing that all up, you are integrating that from minus pi to pi, and then you are averaging it by dividing by 1 over 2 pi. So that's like the mean squared error. Right? And of course, you are only going from minus pi to pi because the Fourier transform is periodic. So whatever is happening from minus pi to pi is enough for you to determine how close your new frequency response is to the ideal frequency response. So that is our criteria, and how should then htn be related to hdn? Well, to do that, let's define a new signal. Let's call y of n equals htn minus hdn. Right? So if I do that, then what is the Fourier transform of yn? What is y of e to the j omega? So by the linearity property, that will simply ht of e to the j omega minus hd e to the j omega. Okay? Now there is another fact that we know from Parseval's theorem for Fourier transform. So what is that fact? That if I take my signal yn, compute its absolute value squared, and from minus infinity to infinity, that is equal to a function in the Fourier domain. So that is equal to 1 over 2 pi minus pi to pi absolute value y of e to the j omega squared d omega. Right? Parseval's theorem in the properties that we studied for discrete time Fourier transform. Now all we have to do is put in the values of yn and y of e to the j omega. So we put in that value, we get n from minus infinity to infinity, htn minus hdn absolute squared, that is equal to 1 over 2 pi minus pi to pi ht e to the j omega minus hd e to the j omega squared d omega. Now our goal was that we want to minimize, we want to minimize this error. Goal is to minimize this, but we have just shown that that is equivalent to minimizing this time domain expression. Right? There is an equality. So that is equivalent to, if we want the new frequency response to be close to the desired frequency response, then the equivalent statement is that summation n from minus infinity to infinity, my new impulse response minus my true or desired impulse response squared should be as small as possible. So this is the statement that I want to work with. Now, if I want, so we are given HDN, design HTN. Now, how the smallest I can make this sum is 0, but of course that requires that HTN is equal to HDN, which means my new impulse response is not finite impulse response. So let's make that constraint. So it's not just that I want to design HTN, but also HTN is FIR. Okay. So let's say that HTN is equal to 0 for all n less than minus m and n greater than capital M. So length, and here M has a different meaning than what we learned in the previous lecture. Here the text uses M for in a different manner. So length of HTN, which is equal to n, is 2m plus 1. Okay? So that's the constraint. We have a filter which is only length 2m plus 1. It goes from minus m to m. What should that filter be? Okay. So let's then write down this expression more carefully. I know that for n less than m, minus m, and n greater than m, HTN is 0. So the statement becomes that I have n less than minus m. I only am left with HDN squared, right, plus n greater than m, I still am only left with HDN squared, plus I have n from minus m to m, HDN or HTN minus HDN whole squared. Now, of course, my new filter that I am designing cannot reduce this, but I can reduce this. Right? How can I reduce this? What's the smallest that I can make this? I can make this whole sum equal to 0 by forcing HTN to be exactly equal to HDN from minus m to m. So then the design criteria becomes that we minimize the error between the new frequency response and the desired frequency response by setting ht of n equals to hd of n for n from minus m to m and 0 otherwise. Okay. So you are given an infinite filter. What you do is actually just chop off the ends of the filter. Keep the filter from minus m to m, and you automatically get the closest filter that you can get to the true filter that you are after. Now there will be error in the frequency response, and that error is going to be proportional to what are the true filter value, the desired filter values that you threw off. Right? The error is proportional to that. Which means that, so what is the role of m in this problem? That the larger capital M is, the smaller the error between the designed FIR filter and the desired FIR and the desired filter, which is not FIR. Okay. Now, there is only one thing left in this discussion, that my filter is not causal. Right? All I did was take my filter, chop it off from before minus m and after m. So I get now an FIR filter, but my filter is not causal. How do I make it causal? Simply shift it by m. So to design a causal filter, my final causal filter Hn is equal to, I simply take my new filter and I shift it by m. So then I will have a filter which goes from 0 to 2m and 0 otherwise, and it will approximate the filter that I was after. So we have learned a basic form of designing FIR filters from ideal filters. What is the, let me just recap that entire discussion. So recap designing FIR filters of length capital M equals to 2m plus 1. Okay. So the first step is, so step 1, you specify the ideal impulse response, HD of n. You start with the frequency response, you compute the inverse Fourier transform to specify the desired impulse response. Step 2 is figure out the length of the filter that you can afford. Capital N. Okay, just 2m plus 1. So you do capital, you are doing n equal to 2m plus 1. That's an odd length filter, which means that you are going after either type 1 or type 3 filter. Okay, because as we discussed, type 1 and type 3 filter pretty much cover everything that you need to do. Now, how do you figure out the length of the filter? It's a function of how much hardware you have available, because the longer the length of the filter, the more multiplications and additions you have to do, because you are using the convolution formula directly. And as we talked about earlier, the longer the length of the filter, the smaller the error between your desired response and the response you are getting. So these are two conflicting requirements. You can make n very large. You are going to get a good approximation to the desired response, but then you have to pay a penalty in terms of the complexity. So, and we'll study that more, but let's just say you figured out what is the length. Then the step 3 is you shift HDN by capital M to obtain HD tilde n equals HD of n minus m. Okay. And then step 4 is, so you do step 3 because you want the causality. But as step 4 is, now you throw out everything. So set Hn equals HD of n minus m for n from 0 up to n minus 1 and 0 otherwise. So these are the 4 steps that you carry out, and this process is called windowing. In particular, this form of windowing is called rectangular windowing. So why is it called rectangular windowing? Because I can write Hn as a multiplication of Hd of n minus m with a function Wn, okay, where Wn equals 1 for n from 0 up to n minus 1 and 0 otherwise. So you have this window which is all ones and then zeros before and after n minus. So at n equal to 0 and n minus 1, it is 1 and 0 otherwise. They are both the same operation. So it's called windowing because effectively after you have shifted your impulse response, which is infinite duration, it's as if you're only looking at a window of that. You're looking through a window which kills off everything else. You can only look through that region. Okay? Everything beyond that window, it's like where this thing is non-zero, this W of n is non-zero, that's the opening of your window. So that's like the window you are looking at, everything else is 0. You are not looking through that. Okay? So it is called rectangular windowing because if you look at this, the shape of this function, it's like a rectangle. And we specify rectangular because actually you can do windowing with other kinds of windows that are not rectangular. And what that gives you, we'll look at that later. Okay? So this is the whole setup of how you will end up designing FIR filters by rectangular windowing method. So we'll do a few examples of designing some common filters using this windowing method. So the common filters are low pass, high pass, band pass, and band stop filters. So let's look at the first example is you are interested in designing an FIR low pass filter with cutoff omega c. Okay. So of course the ideal filter is the following. It is 1 for all values of omega less than or equal to omega c, 0 otherwise. So we know what the filter looks like. Ideally, from minus omega c to omega c, it is 1, then it's 0 up to pi, and then it repeats itself. And we know that if we take the inverse Fourier transform of this, then the impulse response hd of n is a sinc function. It's given by sine omega c n over pi n, and where n goes from minus infinity to infinity. So this is the classical case of we are dealing with a filter whose impulse response is infinite. We really want to design a finite impulse response filter. Well, if we just follow the steps, so this is just the step 1, okay, that we talked about. Step 2, let's just assume, again, right now we are not going to talk about how do you pick that length, but assume that someone said it should be a length n equal to 2m plus 1 filter. So that's done. Then what you do in step 3 is you shift the filter by an amount m. Shifting is being done because you want a causal filter. So hdn minus m, which is simply equal to sine of omega c n minus m over pi n minus m. Of course, this is still an infinite length filter. And the final step, which is the windowing step, is that you only use the values from 0 to n minus 1. Set everything else to 0. So you set sine, you use this function n minus m over pi n minus m from 0 up to n minus 1 and 0 otherwise. And that is your filter. It's going to have a frequency response h of e to the j omega, which is of course not going to be the same as hd of e to the j omega, but it will be as close to it as possible. Okay? The second example is, you could say we are interested in an FIR high pass filter with cutoff omega c. So again, in that case, the desired frequency response is, I want to make sure it's not at this, it's not otherwise, it's up to omega c, omega between omega c and pi. Okay, so this is a high pass filter. It's 0 up to the cutoff frequency, and then it is 1 for the cutoff, between the cutoff frequency and pi. So the filter looks like it's minus pi to pi, 0 at the cutoff frequency. So this is omega c, this is minus omega c. Now step 1 is, so this is our step 1. We know what the response we want ideally, and we go to the impulse response hdn, and hdn is simply given by 1 minus omega c over pi for n equal to 0, and minus sine of omega cn over pi n for absolute value of n greater than 0. To see how to obtain this impulse response, the easiest way is to actually notice that this hd of e to the j omega is simply equal to 1 minus, and let's call that a low pass filter with a cutoff of omega c e to the j omega. right? So then the impulse response of that is simply equal to 1 minus the impulse response of H low pass of N. Now we already saw what is the impulse response of the low pass filter. If you plug in the values, you get back exactly this formula. Okay. So most filters that look like boxes actually can be derived by just posing them in terms of the low pass filter. So this is delta of N, not 1, and that's why you have 1 minus omega c over pi for n equal to 0, but for n not equal to 0 it's simply the negative sign of whatever you get for the low pass filter. So step 2, again, someone came and told you you want to work with a filter of length 2m plus 1. Step 3, you simply shift your filter by an amount m, which is simply equal to, so n equal to 0 goes to n equal to m. So what you get is 1 minus omega c over pi for n equal to m instead of n equal to 0, and then you get minus sign of omega c n minus m over pi n minus m for n not equal to m. Yeah. And then the step 4 is you do the windowing operation. So you restrict that only from 0 to m to n minus 1. So step 4 is simply you say hn is basically 0 for everything except 0 to n minus 1. So it is 1 minus omega c over pi for n equal to m, because m is less than n minus 1. It is minus sine of omega c n minus capital M over pi of n minus capital M for n equal to 0, 1 up to m up to n minus 1, except n equal to m, and it's 0 otherwise. Okay. So the same 4 steps you always follow, and the major challenge you always have is simply computing the impulse response of the filter that you are interested in. Okay. So after this example, I'm not going to carry out steps 2, 3, and 4 because they just work trivially the same way. The third example is FIR band pass filter with cutoff frequencies omega C1 and omega C2. Again, if you look at the frequency response of that is simply equal to 0 for absolute value of omega less than omega C1, 1 for omega between omega C1 and omega C2, and then 0 again from omega C2 to pi. Okay. And once again, the way to think of this band pass filter is through 2 low pass filters, subtraction of 2 low pass filters. If you look at the Fourier transform of this band pass filter, it is 1 from omega C1 to omega C2. And if you think of it, that is equivalent to a low pass filter It is equivalent to a low pass filter with a cutoff of omega C2 minus a low pass filter with a cutoff of omega C1. Okay. If you subtract the two, you get back your band pass filter. Right? So this means that HD of e to the j omega is simply equal to a low pass filter with omega C2 cutoff minus a low pass filter with omega C1 cutoff. And now you just take the inverse Fourier transform. So the impulse response that you are looking at is HDN equals sine of omega C2 n over pi n minus sine of omega C1 n over pi n. From minus infinity to infinity. And now you can just simply window it to get a finite impulse response. The next example is that of an FIR filter, which is a band stop filter. FIR band stop filter with cutoff omega C1 and omega C2. So the band stop filter's frequency response is given by it's 1 and then it's 0 bit in the band, omega C1 less than or equal to omega C2, and then it's 1 again. Okay, so now you want to write down the Fourier the impulse response of this filter HD of n. So the frequency response of this is actually simply equal to 1 minus a band pass filter with cutoffs omega C1, omega C2, e to the j omega. We already saw the impulse response of that, so all we have to do is just plug in the values, and what we get is because of delta so in first Fourier transform of 1 is delta n, so we get omega C2 minus omega C1 over pi for n equal to 0, and for n not equal to 0 we simply have a negative sign, so the order of the sinks get changed. We have omega C1n over pi n minus sine of omega C2n over pi n for n not equal to 0. Again, an infinite impulse response, and all we have to do is simply replace that by a windowed version to get a finite impulse response. The last example is an FIR multi-level or what's called a multi-band filter. So this is a filter which actually is the most generic. So if I just plot it, the frequency response of this filter, from 0 up to pi, what this filter says is, well, let's divide it into a total of L bands. Okay. So you divide it into a total of L bands. The first band is omega 1. So omega 0 is 0. Omega 1, you have omega 2. And then the last band is omega L equal to pi. And you can say, well, my filter takes certain value in the first band, then another value in the second band, then it keeps on changing its value. And these values are given by, for example, this is A1, this is A2, this is A3. Okay, so it's the most general form of a staircase kind of a filter. This is a kind of filter that you would implement if you were designing, for example, an equalizer. Okay. So mathematically, this filter is given as this is equal to some value ak for omega k minus 1 less than or equal to absolute value of omega less than or equal to omega k, where k goes from 1 up to L. Okay. And the convention is that omega 0 is equal to 0 and omega L equal to pi. Now it's very easy to write this also in terms of sums of and subtractions of low pass filters, and if you go through that analysis, it turns out that the impulse response of this filter is simply given by L from 1 to capital L, AL minus AL plus 1 times a sinc function, sine of omega Ln over pi n, okay, for all values of n. And again, if you want to compute a finite impulse response, you simply limit it to a certain value. And there are other types of general filters. Other filter types are other filters with analytical expressions. They include 90-degree phase shifter, differentiator, and so forth. They are given in the text, but the basic idea is the same. Once you compute the impulse response, then you select a value of the length of the FIR filter that you are interested in, and then you window it. Okay? So the main challenge in all of this window method is, the main question is, the only design parameter that is in our hands is the length of the FIR filter. So the question is how to select the filter length capital N. And that, of course, is determined by the fact that how does the filter length affect your approximation to the FIR filter. Now, before we go towards that discussion of how to select the length, I just want to tell you, for example, in this filter design and analysis tool in MATLAB, how does the filter length play a role? How does the windowing method come into play? So if you open it, you can of course tell it you want low pass, high pass, band stop, or there are other versions, differentiator, multiband, and so forth. Let's focus on low pass. Then you say I want a FIR filter, and you see there are so many ways of designing FIR filters. We are only learning about the window method. Okay? So when you do the window method, and then you get to decide what is the order. So order is filter length minus 1. Okay? So if we want, let's say we want a filter of length 64, okay, of length 65, so that's order 64. And then there is another option, which is which window you want to use. Now we have not discussed about different windows. We have only learned about this rectangular window. So we select that. Then we look at which frequency we want. Omega c, this is multiples of pi. So we say omega c is 0.25, so pi by 4. I say design the filter. And this is the magnitude response you get. Of course, you see that this is not that perfect, the ideal magnitude response that you want, and it is because you approximated that infinite length filter with a length 65 filter. Now you can go and look at the impulse response, and you see that indeed the impulse response looks like a cutoff sink, which is what we were designing. We took our sink, we shifted it to 32, right? And then we just cut it off after, from before 0 and after 64. So this is what your impulse response looks like, exactly like a sink. Okay. I could change it to a high pass, keep other descriptions the same, and now you see that what I have is that 1 minus the formulation. Again, I'm looking at the negative sink function, which is just cut off. So we go back to the same point. How do you pick the length of the filter or the order of the filter in FDA tools? So order is equal to n minus 1. So in that example, I put in 64. Is 64 a good number? Is 128 a good number? How should we pick it? To understand that, we should look at the effect of windowing on our desired frequency response. So let's look at the windowing operation in frequency domain. So windowing is saying that I compute my finite impulse response filter by taking an infinite length filter and multiplying it with a window with a function that becomes 0 after a while. Okay. Now what is the effect of this thing in the frequency domain? So HD of n minus m, for that we have to first say what are the frequencies of each of these functions. So HD of n minus m is of course simply my desired frequency response times a phase shift e to the minus j omega m. Now W of n, that is my window, has an impulse response W, or in this case, so it's W of e to the j omega. Okay. Now let's first start with the case of the rectangular window. So a rectangular window is simply 1 for all values of little n up to n minus 1. And so I'll call its frequency response as psi r e to the j omega. Right? Now, what is the frequency response of this window? So it's a box in the time domain. So in the frequency domain, it will have what kind of a shape? So it is the sink-like function which takes the sine over sine form. Okay, it's given by sine of n by 2 omega divided by sine of omega by 2. Okay, because you are in discrete time Fourier transform domain, which is periodic. Now, of course, this is the case when your window is symmetric around 0. We shifted the window to a factor of m, so we also get an e to the minus j omega m factor. Okay. Now, these phase differences are only due to a time shift, so for the time being I'm going to ignore them. I'm not going to take them into consideration. So let's ignore these for the time being. Okay. So what we are interested in is the following. We are asking when we limit our infinite length filter to a finite length, what is the effect on the frequencies what is the effect in the frequency domain. Now, so our new frequency response is h of e to the j omega. In the time domain, we know it's, and we are multiplying two functions, right? So how do I write this as a function of the Fourier transform of my time domain signal? So in the frequency domain, that is equivalent to taking the Fourier transform of this signal and doing a periodic convolution of that with the Fourier transform of Wn. I'm being sloppy here because I'm ignoring the phase factors. Okay. Now what is periodic convolution? It is simply equal to convolution where you are going over one period. So that is equal to 1 over 2 pi uh, 1 over 2 pi factor here, 1 over 2 pi minus pi to pi, right? So you fix one variable and you flip the other and then you shift it. So the convolution expression exactly, except that the limits of convolution go from minus pi to pi. Okay. So what is happening here is, if you look at, so let's take the case of a low pass filter. So your HD of e to the j omega was this ideal low pass filter with cutoff of omega c, and then the Fourier transform of your window function has this sink-like shape. It has the sine over sine property. So if I just compute the absolute value, it takes this form. So now what you are doing is you are going to convolve periodically, which means you just take one period. So this is minus pi to pi. Okay. So you are going to have a periodic convolution of the two. The effect of this is going to be twofold. There are going to be two effects. One is, so what is h of e to the j omega? That there are going to be two effects. I'm going to blow up the region from minus pi to pi to clarify those effects. So this is what first effect is, that instead of the roll off at omega c, the cutoff being very sharp, what you see is a smoothing of that cutoff. So if your original filter was this, your new filter is going to have a smooth transition. It's going to have a smooth transition. Okay, so this is smoothing effect. Okay. And that transition is a function of this thing, which is called the main lobe of your window, of the Fourier transform of your window. Okay. No matter which window you use, in this case we have looked at the rectangular window, but whichever window you use, the main lobe of this window determines the smoothing of the cutoff frequency. Now, the other effect is that because you see that you have these small ripples of your window's Fourier transform, these are called side lobes. Now these side lobes, what happens is that they cause ripples in your new Fourier transform. So instead of your new Fourier transform being straight line, what you get is some sort of rippling effect instead of one. And also where your Fourier transform becomes 0 in the ideal world, in this finite impulse response world, your Fourier transform also has ripples. So this is what your new this is what your new frequency response looks like. So it has smoothing and it has ripples in the pass and stop bands. Okay. Now let's look at the case of the rectangular window more carefully. So focus on the rectangular window. The Fourier transform we saw W e to the j omega for rectangular window of length n equals 2m plus 1. Well, if you look at that, that is sine, I wrote it earlier, 2 sine n by 2 omega over sine of omega by 2. Okay. So let's look at the absolute value so that we don't have to worry about the phase. And if I plot that, so this is from minus pi to pi. It turns out that the height of this, so this is the magnitude response of the magnitude of the Fourier transform of your window. The height of this is 2m plus 1, which is equal to n. Okay. Now it hits the first time it hits 0 around the 0. This point is 2 pi over n, and this point is minus 2 pi over n. So in the language of windowing, this thing is called the main lobe width. Written as delta ml, and that is equal to 4 pi over n. Okay. Now, what is the function of main lobe width? The transition we talked about, there is a transition of this cutoff frequency, right? The transition is a function of the main lobe width. So transition around omega c is directly proportional to the main lobe width, which means that the transition is sharper if delta ml goes down, right? So the smaller your main lobe width is, the sharper your transition is. Now, what is the main lobe width a function of? So main lobe width is a function of the length of your filter, and it's inversely proportional to the length of your filter. And that's where the length of the filter starts coming into play. If we want the transition to be sharp, then this means that N has to increase. The transition goes down inversely proportional to is inversely proportional to the length, so the transition is sharper directly as a function of how much your length is. Okay, you increase the length of your filter by a factor of 2, your transition is faster by a factor of 2. So then the rule for selecting the length of the filter is it should be big enough so that the transition of your filter satisfies your requirements. Now let's look at the peak side lobes. So these are the side lobes, and the side lobe with the highest magnitude, so let's assume in the case of the rectangular window, that is the first side lobe. Okay. In the case of the rectangular window, the first side lobe has the highest magnitude, highest height. This is called the peak side lobe. Now the peak side lobe determines how big is the ripple in your frequency response in both the pass band and the stop band. So if your peak side lobe is high, then your ripple will be high. So if you zoom in onto the frequency response of a filter that you designed by the windowing method, let's say this was your ideal filter, omega C. What will happen is that you will have ripples around 1. Okay. And then you will transition, and even here you will have ripples. Okay. The size of these ripples so let's say this is the size of the ripple from your ideal length, that's called delta in the pass band, and then there is a size of the ripple in the stop band, that's called delta S. Okay. Now in the case of the rectangular window, delta P is equal to delta S. Now the size of these ripples is a function of, it's a function of the peak side lobe, but not just the peak side lobe. It's really a ratio of the peak side lobe to the main lobe height. So it's a function of the ratio of the peak side lobe height to the main side lobe height, to the main lobe height. Okay, so it's really looking at what is the ratio of this divided by this, rather than just looking at the absolute value of the peak side lobe. Okay, so the term that this delta is directly proportional to peak side lobe height divided by main lobe height. And the side lobe in the height of the side lobe is always therefore described as a fraction. It is given as 20 log 10 of peak side lobe divided by main lobe. Okay. So this is just a better description of what I just, graphical description of what I just said, which is that windowing is effectively you take the periodic convolution of your ideal filter with the frequency, the discrete time Fourier transform of your window, and when you do that, the two effects are clear on this picture. One is the transition is not sharp enough, and the other is you have ripples in both the pass band and the side band. And then we already have discussed that if we want the transition, if we want this transition to be sharp, then we better have longer and longer length of our filter. Now let's talk about what role does the length play in terms of the size of these ripples. So going back to the aspect of how do we then select the length of the filter that we can control the size of the ripples, actually that's where things get interesting. We get what's called the Gibbs phenomenon. That no matter what is the length of your filter, the moment you go from the infinite length filter to a finite length filter, doesn't matter now what is the length of your filter, 1,000, 2,000, 500,000, a million, the size of the ripple for a fixed window, for a window, for example, here we are talking about rectangular window, the size of the ripple actually can never be reduced. Okay, so what this says is that regardless of the length of the filter, and the filter length and the window length are the same, so we can say, or length of the window, and the cutoff frequency, both ASL and delta remain the same for the same type of window. Of course, these values will change. The peak side lobe height will change, the main lobe height will change, but the ratio remarkably will stay the same. And because that ratio will stay the same, the size of the ripples in the final frequency response will always be the same. Okay? And in the case of, so for rectangular window, which is the only window that we are talking about so far, the side lobe height is always 13.3 dBs. Okay, so it is always 13.3 dBs below the main lobe. Okay. So it's a ratio, it's always 13.3 dBs below the main lobe, but it is not a function of n. And equivalently, the ripple size or the maximum ripple size, because the ripple is not constant always, is always 20.9 dBs. Okay, which means that it fluctuates with a, so it's not, the error is 20.9 dB from wherever you want it. If you are looking at 0, it's not going to be at 0. And if you're looking at 1, it's not going to be at 1. The height will be the ripple size maximum will be 20.9 dBs. Okay. So for rectangular window, if the ripple size stays the same, then the only thing that determines the length of the filter for a rectangular window is the transition width. Okay. Transition width is where it starts going down and then gets closer to 0. Okay. And transition width is given is proportional to as we talked about, it's proportional to 4 pi over n, which is 4 pi over 2m plus 1. Okay. So that's the only thing then that is in your control. And we try to then design a filter which satisfies the transition width. We are not going to be able to do anything about the ripples. So when people design practical filters, practical FIR filters, they understand the fact that you are actually not going to have a very sharp cutoff, and you are not going to have a perfect 1 and a 0 or a perfect 2 and a 0 in the stop and the pass band. So instead of that, what happens is people describe that the cutoff, instead of describing a sharp cutoff, they say that the filter should be within plus minus delta p up to some value WP or omega p, and then it should get within delta S of 0 after some value omega S. Okay. So this omega S minus omega P is called the transition width. Omega S minus omega P is the transition width. Okay. And in most practical cases, it's fine to just think of the ideal cutoff as omega S minus omega P divided by 2. Okay. So for example, someone will come and say, I want the transition is from 0.1 pi to 0.2 pi is my transition width. So if you were to now start with an ideal low pass filter, then you would say, well, my ideal low pass filter, I should start with an ideal low pass filter which has a cutoff of 0.15. So, sorry, it should be omega S plus omega P divided by 2. Okay. So you will say it's 0.1 plus 0.2, 0.3 divided by 2 is 0.15 pi. So you will define, even though there is no notion of cutoff now, because it's a transition, it's not a sharp thing, you can define the cutoff to be the average of the two numbers. Okay? And the idea is that before omega P, it has to be within this region, and after omega S, it has to stay low enough. That's the definition of omega S, omega P. Now for a rectangular window, it turns out, so a rectangular window has both the ripples. So these are called pass band ripples. Pass band ripple is basically the ripples where you want things to be 1 or 2 or something non-zero, but it's not exactly a constant. And stop band ripple is where you want things to be 0, but they are not really 0. Okay. And a rectangular window has both the ripples of the same size. So omega delta P delta S is equal to delta. Okay. So the main message of the filter design using window method is that A, you don't end up with a sharp cutoff frequency. That's one main message. The second message is that you don't have constant magnitude in either the stop or the pass band. Okay. Those are the two key things that happen. Now for a rectangular window, you have the ripple size is exactly the same, and we know that for a rectangular window also that the ripple size is unaffected by the length of the window or the length of the filter. It's only affected by the length of the filter only affects the transition width. The longer the filter, the smaller the transition width, but the price is you are now using more resources, you have more numbers to store, more computations. So we'll quickly go through this example where we indeed convince ourselves that that is the case. We'll work with, first let's work with a length 16 filter. And since we have only studied rectangular windows so far, we'll just stick with rectangular window. So we say we want a cutoff frequency of 0.2. We design it, and you see that if you zoom in, this is not of course constant in the pass band, and of course you have a transition. You don't have a very sharp cutoff. It's not that it is 0 dBs up to 0.2 and then it goes to 0. Rather, if you look at this point, the ripple, so this is in dBs, the ripple is always 20.9 dBs, okay, which is what we talked about. So this is this is 20.9 dBs below your peak, okay, but it doesn't go down to 0. Now let's increase the length. What we want to see is, does the ripple size get smaller or not? So we studied that the ripple size shouldn't get smaller as I increase the length. The only thing that should happen is where the transition is happening, that should become closer to 0.2. So let's make that 32. I have increased it by a factor of 2. We expect the transition width to reduce by a factor of 2. Okay? We do that, and if I just stop the scaling, it's again minus 20.9 dBs. The height stays the same, and the transition width has gotten closer to 0.2. Right? I double it again, and you see that the transition is getting closer and closer and closer to 0.2. But this first ripple stays at 20.9 dBs. It's not affected by the length of the filter at all. We double it again. It has become even better in terms of the transition. Now it's really looking like a very sharp filter. But the ripple, the main ripple, still stays the same. So whether we can live with this ripple size or not is really a function of the application that we are dealing with. In some cases we can, and in some cases it turns out that we actually want ripples which are smaller than 20.9 dBs. If we want that to happen, if we want ripples that are smaller than 20.9 dBs, that we have to replace our rectangular window with a different window, which will be the topic of next lecture.